Hello and welcome to the Brightics AI Accelerator tutorial series. This is episode number 4, an overview over the PyTorch framework.
Hello, I'm Matthias from the Brightics AI Accelerator team. In this short video, I would like to show you how you can accelerate your PyTorch machine learning scripts using the Brightics AI Accelerator. For this, I'm going to launch a session of a Jupyter Lab environment, which includes PyTorch. I already did that before, so I can jump right into this PyTorch demo notebook. There we'll go into the shared dir, the sample notebooks, to open the PyTorch examples. And I'm going to use the first example, which creates a simple model and uses the MNIST dataset. In the following, I will go over each cell and explain what's happening in each of them. In the first cell, we only import the SBrain libraries, which gives us access to the SBrain API to talk to the backend. In the next cell, we define our input data as well as our model. The input data is defined in the input function. It's basically just a torch dataset, which as usual implements a getItem and a lang method as well, which is special for SBrain, method that returns the batch size called getBatchSize. Then it just returns either a training version or a testing version of that dataset, depending on the parameter mode. Other parameters to this input function are the batch size as well as a parameter which is user-defined. And we will see this in a different video. Next comes the model function. The model function defines the PyTorch model itself. First, we initialize our layers and we connect these layers in the forward path. So we create for an input X and output depending on our layers. Then we create an instance of that model and return it to the calling function. We also need to define an optimizer here, which gets the model parameters, and we also define a loss function, which we also return to the calling function. This wraps up already our definition of our dataset and our model function. The next two functions further define the training and the evaluation phase of our training script. In the training step, we get the model, the optimizer, and the loss function, as well as data, input data, and a target. And we apply the model to the input data, apply the loss function, compute the backward path, and do an optimization step. This is the usual way a PyTorch training works. In the test step, we have the chance to evaluate our model, and we get the model as well as the input data and training labels, and we can apply that model and compute the loss and compute an accuracy which we give back so we can monitor it later. The previous cell contained code which is very similar to the usual training script that we write up in PyTorch. The next cell is specific to SBrain and defines our experiment as well as the configuration of that experiment. So first of all, we define a classifier using our model function. That classifier, together with a name and a description, is used to create an estimator. This estimator is then used to run an experiment. The experiment is configured in the run config. Here we can define the number of workers, which is here 2, as well as how often we want to create a checkpoint or write a summary into the TensorFlow board, Tensor board. We also can define if we want to do an evaluation and if we want to run this on GPU and in a synchronized manner, which is the default for the Horvath training. Additionally, we have to give hyperparameters which defines how many iterations we want to run the training, what is the batch size, and also we define variables that will be used to configure our optimizer. Next, we run the experiment, give it a name and a description, and give all the parameters we defined in the top. Each experiment could potentially consist of multiple jobs, but because this is a single job experiment, we can get a job ID using the method getJobID. Next, I'm going to run all these cells that we have visited so far to run the experiment. And we see here that we get the learning job ID 94, which we can use to look up our experiment in the list of jobs. We see that it is waiting for another experiment to finish, or if we have enough resources, it will spin up right away. We also have the opportunity to look at the tensor board to see the progress of our training. Here we can see the loss and how it is converging. We also get the opportunity to have a look at the log files that are created, where we can see important debug information of our training. We see that the status has changed to succeeded, and we can continue with the notebook. So the job has finished, and we don't need to wait further for the experiment. Now that we have completed the job, we have a trained model that we can use to do some predictions. To do these predictions, we need input data, which we define in the prediction input function. This looks the same as the input function for the training, only it gives just the test set. So it also returns a PyTorch dataset. Further, we need an output function that collects the output that the model gives us and then processes it further. In this case, we serialize the data and encode it into UTF-8 to safely send it back from the endpoint which is running the inference to our notebook. I further defined a visualization function to better visualize the output. For the inference, we have two options. The first is a raw prediction. So we first get the model from our job and then deploy it under a name, which gives us a model endpoint. This needs to spin up a Docker where this endpoint is located, so we give it some time to spin up. Then we do a raw prediction using that endpoint, given our prediction input function and our output function. After running the raw prediction, we will need to decode the serialized NumPy array. And we print it here to have a look at the raw data. We can also visualize that using the visualize function I defined here to get the input data as well as the predictions which match the images we see. Another option is to run an inference job. In contrast to the raw prediction, this is meant to run a job which is expected to run for a longer time. So we don't have to keep the notebook open, but we can also save the output of the model directly onto disk or somewhere else. Therefore, we define a different output function which collects the output from the model and saves it to a text file. Then we submit the job, give it a name and a description, as well as the previous input function and our new job out function. As before with the learning job, we get a job ID that we can use to look up the job in the workbench until the notebook waits for the job to finish. So we know that the job ID is 22 and we can search for it here at the end of the list. And we can have a look into the log file of this job as well. And it already finished. So we can have a look at the text file, and it contains the same predictions as before. This was a short overview of the capabilities to accelerate your PyTorch script using the Brightics AI Accelerator. Thank you for watching this video.